Yeah, that's good. Yeah, now we are recording. Very good. So, Bobak, you will pay attention to chats, right?
Okay, sure. Yes.
Very good. So, hi guys. So, are there any questions from last lecture or in general? Of course, you can always send me emails or just ask questions, but just beginning of the lecture, maybe I should ask. Okay, so I think it was suggested, as I said, that we should take a break. So we'll take a 5 minutes break, maybe up to 7 minutes or something, just to refresh. I think it's a good idea to just refresh a bit. So as I promised, I'm going to do this Milnor's counterexample today. So to do this, we have to talk about flat tori, and to talk about flat tori, we have to know a little bit about lattices, not too much, but just a little bit about lattices. So definition, I would say an Euclidean lattice in Rn. It's a discrete abelian group gamma inside Rn, which is co-compact. So co-compact, of course, as you know, it just means that Rn mod gamma, the quotient of this subgroup is compact in quotient topology. Of course, well, I mean, abelian is redundant because it's a subgroup of an abelian group, sorry. It's a discrete subgroup, I would say, gamma, and subgroup of Rn is just, Rn is a group after R is an abelian group, so this is a subgroup. But it has to be discrete, and discrete is clear. In the induced topology, it's discrete, so that's... Okay, so that's the definition, and that's the explanation, maybe. But there are many other definitions equivalent to this, which is good to know, and some of them we will use. So, yes. So let me just give it like a lemma. It's an elementary lemma, but I will give it to you. So, so the following are equivalent. The following are equivalent. One is that gamma in Rn is a lattice two, there exists a basis A1, A2, An of Rn as a vector space such that gamma is equal to Z A1 plus Z A2 plus Z n. Okay, and maybe third one, that's not very important for me, but maybe the third one I just put, yeah, gamma is discrete. And free abelian group of rank n. So these are three definitions that are equivalent to each other. So this is a very standard result from general topology. You can even prove it. For us, more or less, the most important property is this property 2 that defines lattices, Euclidean lattices like that. This set A1, A2, AN is called a primitive basis for the lattice. So this is called primitive. So these vectors, if you want, are called primitive basis vectors. One thing we have to notice, so let me give you some examples before going and doing anything else. Just, of course, the simplest examples you can take are just, so examples. So 1, of course, you can take n equal to 1 and gamma equal to AZ inside R. So A is any positive number. So this is 0, this is A, this is 2A. Okay, and this is minus A, and so on, minus 3A. So basically, any lattice, one-dimensional lattice, is of this form. And in the sense of isometries of lattices, which I did not define, but you intuitively you know what it means. Two such lattices are isometric if and only if the corresponding A's, which is positive, are the same. So we know everything about one-dimensional lattices in this sense. So that's pretty easy. But starting from dimension 2 and going to dimension 3 and higher, things starts getting very, very complicated. But we don't have to deal with all those complications. So let me just look at dimension 2. We can think of, say, a rectangular lattice. So in this case, gamma is equal to Z E1. So sorry, Z A E1 plus Z B E2. So basically, what we are doing, we are choosing some scales, although this is very bad. So this is A, and this is B. So A and B are positive. Okay, so we just define your lattice in R2 like that. So these are your lattice points. Okay, so this is a rectangular lattice, and if A equal to B, it's called a square lattice. Well, I mean, in this case, of course, you have in 2 dimensions, you have this hexagonal or triangular lattices, which are kind of more fun. So maybe I draw one picture of this. Again, we don't need all this detailed information even at this level, but it's kind of because I talked about it, so maybe mention. Okay, so hexagonal. It's also called triangular. I mean, you're saying. lattice. So you can just think like this. Okay, and then just go like that. So now what I did, my God, okay, so I'm missing one here. So, okay, so this. This would be in the center, something like that. So this is not quite to the scale. So one way of painting the plane with these hexagons, and then there is one more element of the lattice in the center, and you go. So you can write down a basis for this actually. There are many bases, but one basis could be, so A1 equal to, okay, A times 1, 0. So this could be 0, and this is your vector A1, and A2 is A times minus 1/2. It's a third root of unity, and root 3, 2, so it's this one. Of course, you could take this as another basis element. That's also possible, but I just took these two. So, okay, so now let me go to 3 dimensions. N equal to 3. Of course, you can repeat this story over there, so you get a kind of box kind of lattice. But then there is something interesting, which is called body-centered lattice, body-centered cubic lattice. Okay, so we can take a cube of length A. So the lattice consists of vertices of the cube. But then what you do inside, right at the center, also you pick an element. And you pick you declare this also at the center to be also lattice. So this is gamma. So in this case, you can see that the basis could be, for example, A1 is like A times E1. So E1, I mean the standard basis. A2 equal to A E2, and A3 equal to A over 2. So we just take this and divide it by 2, so you just end up right at the center. This is one set of primitive vectors, right, for this gamma. So the lattices, of course, are very important in physics. This is what crystals are all about. The physics of crystals starts by studying this classification of lattices and all kinds of interesting things. Interesting problems in quantum mechanics also are related to this. But okay, so we don't have to deal with that right now. So some notions I want to introduce. One of the concepts is the volume of a lattice. So maybe I erase this here. So volume lattice inside, and so this is by definition it's the volume of any parallel pipe that's generated by a set of primitive basis vectors. The volume of the parallel pipe generated by any set of basis vectors for gamma. So in other words, if we just write, we can write gamma equal to Z A1 plus Z A2 plus Z AN. Then in this case, the volume of gamma is equal to absolute value of determinant of this matrix. So we just take these vectors A1, A2, AN in Rn and write them as column vectors and compute the determinant of that matrix. So this is the determinant of, say, A1, A2, AN. And this is exactly the volume of the parallel pipe generated by A1, A2, AN. This determinant, you take absolute value, which is the non-signed volume, and that's it. Now, the question is, of course, is this independent of choice of basis vectors or not? And the answer is yes, it is independent. Choice of basis vectors I mean, the reason is that if you have any other basis vectors, then they are related to each other by a matrix which is integer value, GLNZ, invertible. Then there exists, so for any basis A1 prime, A1, AN prime of gamma, so if you can write like that, then there exists A belonging to GLNZ. So these are invertible matrices, and by matrices which have integral entries, such that AI prime is equal to AI, right? So this is. You see, this is, you just write this equal to Z A1 prime plus Z AN prime. And from here, you get that there exists an integer value. Yeah, it is. Okay, now, because this guy is invertible and is integral, so immediately you get that absolute value of determinant of A is equal to 1. So if you change this matrix by multiplying these columns by another matrix, the determinant is multiplicative, the absolute value of determinant is 1. So this is independent of choice of basis for lattice. Some references, they call it co-volume of gamma. That's also an appropriate name because, in a sense, this is really the volume of the quotient space in some sense, in some natural measure on the quotient space. So that's really co-volume. So it should be.
There's a question.
Okay, yeah, please, yes, louder, please, if you can.
Just to confirm, this parallel pipette is a fundamental domain.
Yes, exactly. Okay. It is a fundamental domain, right? It is, but not all fundamental domains are of this form of parallel pipes. There are more interesting fundamental domains like Wigner-Seitz or Dirichlet fundamental domains, which I don't think we needed, but some of them are of this form. Yes. Yeah.
In every lattice, does there exist a fundamental domain that is a parallel pipette?
Oh yeah, absolutely. Just choose a basis. Then you get this D, for example, D equal to the set of all the T1, A1. plus Tn An such that Ti is between 1 and 0. This is a
Okay.
fundamental domain.
Okay. Thank you.
You can always, that was a good question. You can always express it like that. So this is one concept we need. Okay, now another concept that we need is the dual lattice or reciprocal lattice. That's also, we need this concept. So dual lattice. So gamma star. Also, let me call it, in physics literature, this is called reciprocal lattice. So this gamma star is the set of all, say, y belonging to Rn, such that the inner product of y and x is an integer for all x in gamma. Okay, so it is, we have defined a subset of Rn at least, which is obviously a subgroup, but then you can check that this is discrete and it's a lattice. So check, I will check it. Check that gamma star is a lattice as well. Well, okay, I mean, if you pick a basis like that, a basis for gamma, we can pick vectors, A1 star, unique set of vectors, A1 star, A2 star, An star, such that they have this property that Ai star, inner product Aj is equal to delta Ij. Existence of these things is clear because you can do the following. You can just go to the dual vector space, for example, pick the dual basis of this given basis, because this is the basis of Rn after all. And then you take the identification of Rn star with Rn using the Euclidean metric to come back down on Rs on Rn, and then you have this basis. So once you have chosen this thing, which is unique, then of course you can immediately show that this gamma star indeed is equal to gamma star is equal to ZA1 star plus ZAN star. So it is a lattice. Another thing that we need to know about this lattice is that its volume is inverse of the volume of our original lattice. That's also easy to check using this relation model. So I just give it as an exercise. I hope Babak is taking note of these exercises and putting it in the file, please.
Okay, sure.
Thank you, Babak. Yeah.
I also had a question because sometimes there are definitions with 2 pi.
Yes. Yeah, these are different normalizations and kind of, there is no agreement which one to choose. I think different people. As you know, there are 4 types of different definitions of Fourier transform, right?
Yeah, that's true. Yeah.
So that's a sign that Satan or evil exists in the world. So there is no canonical choice. I mean, it's really, it's bothersome. I'm with you. I feel you. Yeah. I mean, it's but that's what we have to live with, unfortunately. Yes, there is that normalization as you wish. Yeah. So exercises that show that. So basically, volume of gamma star is equal to volume of gamma inverse. Now, a lattice is called unimodular is called unimodular if its volume is 1. Right? So example, of course, I mean the following lattice, for example, gamma, you know, a z plus 1 over a z. This lattice has fundamental basis vectors a e1 and 1 over a e2, and so it's a basis vector for this, so volume of gamma is 1. So just simple computation for reciprocal lattice. For example, I'm now thinking of just simplest case, gamma equal to az. So then gamma star is equal to 1 over a z. So the reciprocal lattice in this case is very easy to compute. Just as a kind of little exercise for yourself, try to compute the reciprocal lattice of that body-centered lattice I gave you. So here is exercise again. Compute reciprocal lattice of the body center cubic lattice. That's what we introduced beginning of the lecture. Okay. There are also face-centered lattices where you pick one also lattice vector right at the center of each face. Those are even more complicated. But then in 3 dimensions, there are even much more complicated cases. So this is now very well known among chemists and mathematicians, of course, geometers. There is a whole book, by the way, by Conway, the late John Conway of Princeton. I think it's called Lattices and Codes, Conway and Sloan. It's a hefty volume. It's 700 very difficult mathematics. It's all for yeah, I mean, a study of lattices. So we'll see some of it. I mean, not that book, but I mean some complications soon. So that's, okay. Any questions or comments, by the way? Oh, there's a question in the chat, it seems. Maybe there isn't. So there is a joke that differential geometry is the properties of manifolds that are invariant on their changes in notation. Yeah, that's. Oh, okay. The changes in notation. That's really funny. Thanks for sharing. How should I pronounce your name? Is it Heng-Yi or
Heng-Yi? Yeah, you got it right. Yeah.
Heng-Yi. Heng-Yi. Yeah. Okay. Yeah. Exactly. Thank you. Yeah. That's nice. Okay. Very good. So now, okay. So now we want to consider flat tori. So So this n is equal to Rn over gamma. By definition, these are these manifolds. So topologically, this is a torus, of course, right? Is a torus. I mean, is an n torus. So what we know is that this n topologically is isomorphic to S1 plus S1 n times. So topologically, I mean, for n equal to 2, topologically it's a torus. That's like a torus embedded in. But metric-wise, though, it's there is a metric here that's induced from Rn. So, but the metric on Rn, I mean the flat metric, Euclidean metric on Rn, so this Euclidean metric induces a unique metric on the quotient such that the projection map, the covering map, is a Riemannian covering map or is a local isometry. Let me tell you. Let me write it. What the flat metric on Rn induces a unique metric on M, which is this one, over gamma, such that the projection map so this projection map pi from Rn to Rn mod gamma. So this map is a Riemannian covering map. So being a covering map is obvious. I mean, in fact, this is the universal cover of Rn mod gamma, right? I mean, pi 1 here is Zn, and that's the universal cover. That's a simply connected manifold. This is a quotient map, is a covering map. So being a covering map in this case is clear. By Riemannian covering map means that, okay, so I'm claiming there exists a Riemannian metric here, unique. And of course, we have the Euclidean metric such that this map is a local isometry. So it's isometry on the level of tangent spaces. From tangent space to tangent space is an isometry, is a local isometry. So how can we see this? That's very easy. You just, take a point in the quotient and lift it here. Take any point here, lift it here. You have infinite number of lifts, right? But this is a covering map. So locally, you have a local diffeomorphism between each of those pieces of pancake, and this neighborhood here. So I'm saying if you have this covering map, you have infinite pancake going up to infinity and minus infinity, so to speak. So each of them is diffeomorphic to this. And what you do, you just pick a Riemannian metric here, using diffeomorphism, you transfer it here. Now the only question is if this is well defined or not, but this is well defined because this group gamma is acting by isometries. The translations are isometries of Rn, so the metric structure here and there are really the same. So you don't lose anything. So that's, you're not creating any ambiguity by this method. So this is well defined. So this is the metric that we are going to work with. And these are called flat tori. So let me write now a general result. So let Mg be a Riemannian manifold. It's a simple result, but it's good to bear in mind, Riemannian manifold. And G, a group acting by isometries on M such that the quotient map from M to M mod G. So that's the quotient manifold through this action. It's a covering map, in fact. So again, in this case, a similar argument as I gave here, it shows that there exists a unique Riemannian metric on MG. M mod G such that this pi is a Riemannian covering map. So again, same argument. So let me give another example. So here is an example, for example. So we have Rn, we have this group gamma acting by translations, which are isometries. Of course, the quotient from topology, we know that again is a universal. In fact, it's a covering map. In fact, it's a universal covering in this case. And that's it. So we induce a metric on the quotient. And here in general also we can do the same. So let me give another example. So take m equal to Sn and take G equal to Z mod 2. So this is the antipodal action, right? Okay, so this is antipodal action, and of course the quotient in this case, M mod G, is real projective space. I mean, P and R, real projective n space. So then we have a metric on this from the round metric on a sphere, right? And this is a metric that sometimes you want to work with. On this projective space, real projective space. So this is a little result, but it's kind of cute and it's really useful. I mean, it gives you many examples of Riemannian metric on quotient spaces. Of course, the group has to act by isometries, otherwise you run into ambiguity. Which lift you're going to work with, you don't know. So, but if the lifts are kind of equivariant with respect to this gamma, isometrically, local isometrically equivalent, it doesn't matter, so you have a unique metric. Any question? So let's see, we have now 40 minutes, so we can stop at 50 minutes, I suppose, or 45 minutes, I guess. Yeah, in 5 minutes we can stop, take a break then. Okay, so now the Riemannian, the Laplacian here. So this delta, so under the standard local coordinates, this delta is going to be exactly same formula because locally we are just using same coordinates. So it's going to be the same formula for the Laplacian in flat space Rn. In other words, delta is equal to minus some e2 xi squared. So C infinity of this guy Rn mod gamma. Okay, I mean, it's a smooth manifold C infinite function, but we can also see it as the set of all functions f from Rn to C or R, such that these are gamma periodic. So, you know, so this is like f of x plus gamma is equal to f of x for all x in Rn for gamma in gamma. So these are gamma. So these are generalizations of periodic functions on the line. So we have these lattice periodic functions. We can work with any of those concepts. Okay, now. Right. So let's compute. So we can think of L2 here. So, okay. Yeah, so maybe I give an example. Yeah, okay, so later. So now we want to look at the spectrum of Laplacian for flat tori. So, so the gadget that we are fixing is this gamma. So now let phi gamma, so phi y of x be equal to exponential. So so let me write it here. Exponential of 2 pi I inner product of x and y. I mean, we can even write it as e to the 2 pi I x dot y. For all x belonging to Rn, and for all y belonging to gamma star. So here we are thinking of this phi y as a function, in other words, from Rn to C. So notice, because we chose y in gamma star in the dual lattice, this function phi y is gamma periodic. So that's nice. Is gamma periodic. That's clear because if you change x by some amount, you know, x plus gamma is equal to pi y of x. I mean, this guy is e to the 2 pi I x plus gamma dot y. That guy is equal to, this is equal to e to the 2 pi I x dot y times e to the 2 pi I gamma dot y. But this gamma is in gamma, this is in gamma star. So this product is an integer, and e to the 2 pi I integer is 1. So this whole thing then is 1. So periodicity follows. You must have seen, if you take like solid state physics, this is used all the time, day in, day out. These are called plane wave functions. Okay. So now we have these functions. At least they are non-trivial. They are non-zero functions. They are on the torus. They are gamma periodic. What is delta? Delta of f5. You can compute the partial derivatives here easily, and this comes out to be equal to actually 4 pi squared norm of y squared phi y. Oh, no. F1, phi 1, phi 1. So yes, that's enough. So we notice that yes, this is now an eigenfunction with eigenvalue 4 pi squared norm of y squared, because y is fixed, y is in gamma star. So that's so yeah, we'll use it to completely classify the spectrum and eigenfunctions and see what we can do with it. Okay, guys, let's take at least 7 minutes break and we'll be back. Okay. So maybe I should pause the video here. I pause it. Okay. All right. So now this kind of functions. So now basic Fourier theory shows now, I mean, again, this is really Fourier series theory. Theory shows that actually, I mean, these functions form, you know, so these functions e to the 2 pi I x dot y, y belonging to gamma star, they form an orthonormal basis. Well, let me put it like this, orthogonal basis. I'm not claiming orthonormality yet. It's not. Orthogonal basis, I mean Hilbert basis, of course. For L2 of Rn mod gamma. So this we know. This is for L2 of this basic Fourier theory shows this. So that's a Hilbert basis. Now, to know whether okay, let me not discuss this orthonormality right now. But from here, then it follows that basically what you found here is a complete set of spectrum. Then I mean, it's a complete spectrum of the Laplace. So this it follows that if you believe in this result, it follows that the spectrum of Laplacian for M is actually this set 4 pi squared norm of y squared for y belonging to gamma star with eigenfunctions e to the 2 pi I x dot y. So in other words, this dual lattice labels the spectrum of the original manifold, and also it labels eigenfunctions. So one definition is the idea of length spectrum. The length spectrum of the Tori, I mean, I can say even the lattice, the set. So basically, we can forget about that 4 pi squared, and we can forget about norm y squared. You just say norm of y squared, where y belongs to gamma. So
Do you mean gamma star, not gamma?
no. This is for, yeah, I mean, of course, it can be for gamma star, but in this case, I'm giving a general definition for any lattice, right? So for gamma, for any lattice, I just say its length spectrum is this number, the set of these numbers. And now I want you to pay attention to the following thing. This length spectrum is exactly the lengths of all closed geodesics in Rn mod gamma. So notice that length spectrum is equal to lengths of all closed geodesics on Rn mod gamma. You see, by a closed geodesic, I don't mean a geodesic that wraps around only once. You can have several times going, right? So you can, I mean, here is like a torus, for example. You can have going around once or twice or 3 times, same here, for example, or other closed geodesics. I mean, proof of this fact is not difficult because, you know, let me give a proof. What is important is to see the connection. Now, for the first time with closed geodesics on this manifold, Riemannian manifold. So proof. So if you pick a closed geodesic, so I would say what would be C on mod gamma. So we have this covering map Rn, and here is Rn mod gamma. So this is so there is some closed geodesic like that. So what you can do, we can just pick a lifting of this initial point here. And then we just do a unique pass lifting because this is in the covering space, right? So we can always, there always exists a unique pass lifting to the covering space. So lift this geodesic to covering space Rn. You may not end up at the same point, of course, but you end up at another point. But what happens is that this is going to be, again, a geodesic, because this map is a Riemannian covering map. I mean, one property of geodesics is that they minimize length, and this map is a Riemannian covering map. So it would send geodesics to geodesics, I mean, under this lifting property and this property. So, but we know what the geodesics here are. The geodesics here are just straight lines. And what we know is that because they end up at the same point, so if this is x prime and this is x prime minus x must belong to the lattice gamma, right? And length of C must be exactly length of this vector. Let's call this maybe a y, which is so this is easy to see that the length spectrum of this Gaussian manifold is exactly these lengths of these lattices. I mean, lengths of geodesics in the Gaussian space. So keep that in mind because this will come up again.
I have a question, please, Masood.
Yes, yes.
So Riemannian coverings are local isometries, right?
Local isometries, yes.
So So are you now talking about like polygon geodesics for these cases? Because it should be pulled back locally and then connect them to each other, right?
Yeah, but no, but I mean, first of all, everything is smooth. So the lifting is smooth, and there are no other things, no other geodesics that move in a smooth way, and it's a geodesic. It's just straight lines. So that's going to be a straight line. There's no problem with that, right?
No, I mean when you pick a geodesic on let's say that torus, each piece of it can be given by the image of a geodesic, not globally.
No, I mean.
Am I right or?
No, I mean any curve, any curve in the quotient has, if you fix a lifting for the initial point, has a unique lifting with respect to that lifting of the.
Oh, okay.
Do that lifting, that's a smooth, and it's locally geodesic, so that's a geodesic. So that's.
Okay, yeah, thank you.
The definition of geodesic also is local because it has to satisfy that differential equation.
Yes.
Right?
Yeah, thank you.
Okay, very good. So we are good. So now what we want to say now is the following. So we want to now construct two lattices that are isospectral but not isometric. So let me tell you the condition for isometry of lattices, and so the goal now is this. Construct two lattices in R16, which are, we're going to show that they are isometric, isospectral, not isometric, you can think it in the following set, i.e. Rn mod gamma is not isometrically equivalent to R16 mod gamma prime. Gamma. Construct two lattices, gamma and gamma prime, in R16, which are isospectral, but not isometric. I mean, everything refers to the manifolds because I did not define the spectrum of a lattice. I just defined the length spectrum of a lattice. But the spectrum of a lattice is really a spectrum of the Laplacian on the quotient space, right? So I want you to understand the whole problem now is a completely lattice theory problem. It's completely turned into a lattice theory problem. Okay. So now the first step is so there is some general theory of these lattices, which is good to know, so it's useful. So let n belong to 8. And so this is the set of numbers 8, 16, 24, so on. So let gamma n, let's define two lattices gamma n, which is the Zn, and gamma 2, the set of all x1, xn in Zn, such that their sum is an even number. Okay, I mean, obviously gamma 1 is is a lattice. This is the kind of quintessential lattice for everyone. So then a gamma 2 is also a lattice. You can check. I mean, this is a subgroup, it's discrete, it's full rank, and da, da, da. So this is also a lattice. That's not a problem. So now also gamma 2, of course, is inside gamma 1, and as a subgroup has index 2. It's an index 2 subgroup. Okay, I mean index 2 subgroup because you know you can write gamma 1 as gamma 2. That's one coset, and then plus another coset would be something like because the sum of these things has to be even, so you can just take. So we need. This is gamma 2, and then if it is odd, yeah, 1, 0, 0 plus gamma 2. This vector is not in gamma 2, and of course, everything you can write as. So this implies that this is index 2. Okay. So this is an index 2 subgroup. And now, what is this gamma n? So let gamma n, that's the main construction, gamma n to be lattice generated by gamma 2, and this Wn, this vector Wn, which is the following vector 1 half, 1 half. So gamma n, in other words, is the set of all, say, x plus k Wn's, x belonging to Zn. No, sorry. X belonging to gamma 2. Sorry, x belonging to gamma 2. It's not Zn. Gamma 2 and k belongs to Z. So these are the lattices that you're going to work with. This gamma n lattices. So now gamma 2 inside gamma n. Of course, I mean, if you take k equal to 0, you recover points of gamma 2. So this is inside, but this is has index 2. Also, since Wn actually belongs to gamma 2. Okay, so if it is even, then you're back in gamma 2, so this is one coset, and if k is odd, this is another coset, and they cover the whole thing, obviously. So this is index 2. As index 2, since this. So that's fine.
Sorry, can I ask a question really quick?
Oh, absolutely, yeah.
Yeah, so Wn is what, like an n tuple of 1/2?
Exactly, exactly.
And so, but k is changing, but n's fixed, right?
Exactly, and it's fixed, yeah, yeah.
Okay.
So
All right.
what you do,
So it could be like gamma kn.
Gamma, yes, yes, exactly. It could be, no, I mean, k is an integer, k is changing.
Oh.
So we just take.
Oh, I see. I understand. Sorry, I get it now.
Oh, that's fine. I mean, in order to construct a subgroup, we are forced to take all multiples of them. Otherwise, you know, if you add 2 of them, yeah.
Right. Thank you.
Sure. Okay, so yeah, very good. So yes, indeed, we just take all multiples, and this is the set of all x plus kwn such that x belongs to gamma 2 and k belongs to z is an integer. So this also has index 2 because of this, as I explained.
Masood, sorry, I have a question as well.
Yeah, sure.
Do we require n to be even? Because otherwise, 2 times Wn has some n.
Oh, I mean, we are requiring actually n to be multiple of 8.
Oh, of course. Yes.
Yeah.
Sorry.
So this will be needed even so more. So yes, exactly. No, I mean, we don't, I mean, right now n is even is enough, but eventually n has to be a multiple of 8 in order to, for everything I'm saying to be correct. Okay. So, I mean, then this index 2 business shows that volume of gamma n is equal to twice volume of gamma 2. This is equal to volume of, because again, gamma 2, here has index 2. This is equal to, it's equal to volume of Zn. That's equal to 1. So what we are using here is that, of course, we are using this general fact that, I mean, so I'm not using gamma 1, gamma 2 in reference to this notation. In general, gamma 1 inside gamma 2 index m, this implies that the volume of gamma 2 is equal to m times volume of gamma 1. The reason for this, this has index m, so it means that gamma 1 and m of its cosets together, they cover the whole thing. So you can start with a kind of fundamental domain for gamma 1, and then take its translates under these cosets, and then get a fundamental domain for the whole thing, and that would be your the volume of the thing. So this needs a little bit of work, but intuitively it's kind of clear. At least I hope. But so I'm using this result here, and of course volume of Zn is 1. So this volume of gamma n to be 1 is absolutely fundamental for us. So it means that this gamma n is a unimodular lattice. It's unimodular. Any questions? Any other questions? Okay, very good. So now we want to prove some properties of the length spectrum of these lattices, lengths of these lattices. So one lemma is this. If y belongs to gamma n, then norm of y squared is even. So remember, n still is in that range, multiple of 8. I don't know. I think we have to use it now. But... Okay, so let's prove this. So let's take y equal to y1, yn belong to gamma 2. So it means that y1 plus yn is even, right? So the norm of y squared is equal to, of course, sum yi squared. This you can write it as sum yi squared minus twice sum yj I less than j, right? So this clearly belongs to 2z. Because this number is even, squared is even, and this is twice, this is an integer after all, so this belongs to 2z. So here we didn't use any property of n to be multiple of 8, so at least this is okay. But these are only part of the vectors in gamma n. So we have to argue with wn and k and the sum. Step by step, you can do all of those. I mean, for example, if you look at, so next case is if y belongs to zwn. So it means y is equal to kw for some integer. y1. Okay, right. So this is equal to k times half, and remember this is multiple of 8. So a normal y squared is equal to k squared sum quarters, I from 1 to n. So this is equal to n over 2 k squared. This belongs to 2z. Now we are using, since n belongs to 8. Now you have covered this case, that case, and then similarly you can cover now the sum. It's elementary. You do this trick sum. It's not a tricky one, it's straightforward. So you just get y plus k. Okay, so the square lengths of these vectors are even. That's very good. Now we have to show that gamma n is not only unimodular, is actually, I mean, okay, unimodularity was easy, but is actually self-dual. In other words, gamma n star is equal to gamma n. This lattice is self-dual. So, lemma, gamma n is self-dual. I mean, is a self-dual lattice, i.e., gamma n star is equal to gamma n. Okay, so proof. So first we have to show. I believe we're going to show gamma n is inside gamma n star. Gamma n star are all those vectors that pair integrally with gamma n. So we have to show that for any y and y prime belonging to gamma n, the inner product is an integer. Belongs to z. If we prove that, then we have done this, right? But let's compute. So y then is of this form, some general form x plus kwn, and y prime is equal to x prime plus k prime wn. So of course x and x prime right place. So inner product of y prime is equal to inner product of x prime plus k x prime wn plus k prime x wn and plus kk prime wn squared. Now, since this inner product xx prime belongs to z, this is now. Okay, so let's start with pieces. This one, this piece, xx prime belongs to z. Since, of course, I mean, in this case, x and x prime actually already in Zn, so that's fine. Also, x prime and wn and xwn are in Z as well. I mean, each piece is there in wn squared. Wn was half, and square it, it's multiple of 8, it's going to be integer. So same with this, forces everything to be integer. So this is elementary, in other words. So that's. So this shows that gamma n is inside gamma n star. Now we show that the index is 1 by using volumes. The volume of both things is 1, so the index must be 1, so they must be equal, right? But let me write it like this: volume of gamma n is equal to 1. So this implies that volume of gamma n star, which is inverse volume, n is 1. So index of gamma n star, gamma n in gamma n star is 1. So they are the same. So that's good. So they have, they are really, okay, so we have this crucial property that this lattice gamma n that we need is actually self-taught. That's going to be very, very important. When we use this Poisson summation formula, we're going to prove a trace formula that relates two things, the lattice and dual lattice. But if the dual lattice is the same, then it means that we have relation between, basically what it means is that we have relation between quantum mechanics and classical mechanics on the same manifold, in this case flat tori. And that will be crucial to derive the final formula. So you will see that soon. So far what we have done, first of all, we have shown that for any x belonging to gamma n, so we have to remember these things, gamma n, norm of x squared belongs to 2z, is an integer. And second, gamma n star is self-duality. So now what we are doing, so our now I can introduce at least these lattices. So the lattices that was introduced by Ernst Witt. So all this work goes back to Ernst Witt. I would think maybe 1940 or something. At least 1940s. Would be good to check that. So the lattices that he took is gamma. One lattice is gamma equal to gamma 8. Index sum gamma 8. This is inside R16. I mean, okay, so we just write it as R8. Index sum R8, which we see that as R16 because this is the. And then the other lattice, gamma prime, is actually gamma 16, which is, of course, inside R16. So these two lattices were introduced again by Witt. And what he showed is that these lattices are not isometric, but they are, basically, he showed that they are isospectral. They have the same length spectrum. So Witt showed that two lattices are not isometric, but have same length spectrum.
Do you mean length spectrum counted with multiplicities?
Yes, exactly. Spectrum counted with multiplicities, yeah. So it really means that, yeah, how many times this appears in one set exactly appears in the other set. So it's like the way we count the spectrum of eigenvalues with multiplicities, yeah. So now showing that they are isometric is a bit tricky, but it's elementary anyhow. So I will give the argument soon. But showing that they have the same length spectrum, it's not elementary. So then he had to introduce theta functions and the theory of modular forms. So he had to use some deep results from modular forms and stuff. Okay, so now the plan is this. I will prove this, and then I will introduce the modular form stuff, and we gain some understanding of that, and then we can start seeing why these two lattices are actually have the same length spectrum. In other words, because these lattices are self-dual, by results that we proved, this just shows that those Laplacians are isospectral, because the spectrum of Laplacian in any of these lattices is parametrized by length spectrum of the dual lattice, right? But the dual lattice is the same. So it means that the Laplacians are isospectral, but then by elementary means, you can show that they are not isometric. So this was the first example, 16-dimensional example. So then people were able to bring this down. I think these lattices, the best result is due to Conway and Sloan. I think they have some 4-dimensional lattices actually in R4 that are isospectral but not isometric. So you can imagine would be kind of harder to prove, I think. I haven't looked at their proof actually, but I can imagine that's much harder to prove. Yeah, bringing dimension takes a lot of energy. Okay, so we will see that at least this original result. And Milnor's thing was he really noticed that this is what you need. So maybe it's time to stop, I guess. Although we took 5 minutes, 7 minutes break, but I think it's a good point to stop. I mean, we covered good ground now, so maybe you ask some questions. I'll be happy to take your questions.
So I have a question.
Yes, yes.
So if we have two manifolds which are isospectral, then let's say, okay, closed manifolds, isospectral, then we can take L2 spaces of these manifolds, and basically by assumption there exists a unitary operator between the two, which intertwines between the Laplacians. And the question is, but since if they are not isometric, this cannot be simply induced by some map, I think. So
yeah.
Is there any actually can we actually construct a nice unitary operator like that? Or?
No, although I mean, actually, yeah, that's interesting you mentioned this, because we used similar ideas for non-commutative tori. You see, what we did was in doing some curvature computations, we wrote down some unitary between this Hilbert space and another Hilbert space. And indeed, we used isospectrality. And in the other picture, it was much easier to understand things. Not so easy, but it's still much easier. But in real usual manifolds, I haven't seen anything like that. But I wouldn't be surprised if that's been used. But no, that's a good idea. Yeah. It's not induced by maps between spaces. That's for sure.
Is there any description other than take orthonormal basis in one and map it to orthonormal basis in the other, like some integral operator or something like that?
Unless you are dealing with very, very concrete cases, maybe like homogeneous spaces of Lie groups and stuff like that. I doubt it if on general manifold you can do a general construction like that. But maybe on some homogeneous spaces of Lie groups, something like that might be. There might be some concrete construction, but I'm not aware of that actually. So I think we have to discuss that a little more actually. Yeah, that's a good question. Yeah. No, I mean, yeah, because you really don't have access to a spectrum in actual spectrum. I mean, really, we don't have access to that. It's like a very, very transcendental object, set of numbers. Still, we don't know almost nothing about the spectrum. I mean, take, for example, take any set of numbers that satisfies the profile of a spectrum of an n-dimensional manifold. By this, I mean it satisfies the Wiles law, for example. That's a necessary condition, right? But then the question is there a manifold whose spectrum is this set of numbers? Nobody has any answer to that. It's a completely open question. It's total mystery, actually. So how to characterize a spectrum of Laplacians or other operators in some fine way such that you can reconstruct. And actually, what sets of numbers are obtained, we don't know. I mean, that's again another. Yeah. Maybe I will turn off the video, recording, and then stop recording.